Let us see the third topic in electrostatics, that is Coulomb's law. So, this is extremely important topic. Coulomb's law is an experimental law, which means in 1785 the French physicist Charles Augustin de Coulomb, with the experiment, gave the relation between the charges, what is the magnitude between the charges. So, this is purely not a theoretical, it is purely this law is purely based on experiment. So, what he did was, he took one long string, a very stiff string, a metallic string, where charges can be given here. So, let us say from a charged glass, you can transfer the positive charges through this cable, whatever cable you have here, and to the edges what you have is two metallic spheres. So, this one, what you call it as torsion pendulum, here torsion balance or torsion pendulum, you can say. It is like this, you have a pen, right? So, you just have a thread to the pen and just twist the pen, it will oscillate. So, more twisting means more force you have applied, more oscillations or more angle it will make. So, based on that logic, in 1785, almost like this is 2025, so almost like 240 years back, he gave this law. So, what he did was, he inserted one more charge, one more cable with another, attached to another sphere, right, another sphere. I will show in a different color so that it will be highlighted like this, and he gave here a positive charge to this externally. So, now if you have both are positives, what will happen? The spheres will oppose each other, which means the twisting will happen in this thread cable. So, higher the twist, higher the force of repulsion. So, based on this, he gave the Coulomb's law. He gave a law that is called as Coulomb's law, as he gave that. According to this Coulomb's law, what exactly it states? Coulomb's law states that magnitude of the attractive or repulsive electrostatic force between 2 point charges. Let us say I have point charge here Q1, another point charge here Q2. So, force of attraction or repulsion between the 2 point charges is directly proportional to product of the magnitudes of their charges, which means F due to electric is directly proportional to Q1 into Q2. So, this is what he gave based on experiments. It is not Q1 plus Q2 based on experiment. No, it's not Q1 by Q2. It's not Q2 by Q1. So, it is exactly product of charge 1 and charge 2 and inversely proportional to the square of the distance between them. So, Fe is inversely proportional to R square if R is the distance between the charges. So, by combining these two, you can write force of Coulombic force is proportional to Q1 Q2 by R square. Take out proportion and give a proportionality constant K Q1 Q2 by R square. So, where K is proportionality constant and experimentally it was found 9 into 10 to the power of 9 and units of K comes from units of force, that is a Newton, and R square you send this side, which means meter square, and then Q into Q square comes this side, which means Coulomb square. So this is the value of K, and actually this is 1 by 4 pi epsilon naught, 1 by 4 pi epsilon naught. So the Coulomb's law actually you can write instead of K, if you want to write the Coulomb's law is this. So F equals to 1 by 4 pi epsilon naught Q1 Q2 by R square. Of course, this is a magnitude. Force is a vector which I will discuss a bit later. So K is 4 pi epsilon naught. Epsilon naught, what is this epsilon naught? Epsilon naught is what you call it as permittivity of free space. Permittivity of free space. The permittivity of free space is a physical constant. A constant. How much is that value? Here I gave 8.8. So approximately 8.8. We write. Actually, it's a big number with errors also they gave. So that's a 10 power minus 12. And the units exactly inverse of the units. So here this is n inverse meter minus 2 Coulomb square, because units of epsilon naught is exactly inverse of K. Okay, so that's a Newton inverse m minus 2 C2. Okay, so this is what exactly the permittivity of free space is a physical constant that reflects the ability of electrical fields. Ability of electric fields, how much electric field can pass through it, how the electric forces can pass through it. That is what you call it as permittivity of free space. Different materials have different permittivity values. If you take air or vacuum, relative permittivity is 1. So relative, what do you mean by relative? So if you have these two charges, let's say in a medium, so then this will change as F equals to 1 by 4 pi epsilon naught into epsilon R. You have to write what you call it as relative permittivity. So epsilon R is what you call it as relative permittivity, which is also called as dielectric constant. Dielectric constant. K is the symbols sometimes we write. So different materials have different values of epsilon R. So for air epsilon R is equals to 1. So whatever you wrote here, this formula is valid for air or vacuum. If you have a, let's say, ice, you kept two charges between ice, then what happens? The force here in this equation, you have in the place of epsilon R, you have to write 5. Number 5 you have to write. If you have two charges in water at 20 degrees centigrade, you need to multiply this with 20, which means compared to air, if you have two charges in air, you have some force F, and you keep two charges in water, then you have 80 is a dielectric constant, which means you have to divide F, divide with epsilon R, which means you need to divide with 80. So 80 times the force of attraction or repulsion in water will decrease. 80 times the force will decrease. So that's what exactly it means. That's what exactly it means. So in vector form, let's see how it looks like, the Coulomb's law, because force is a vector. So how it looks like, let's see. So if two charges on a line, let's say I have like this Q1, charge 1, charge 2, the distance between them is, let's say, R12. Now force on Q2 due to Q1, and both, let's take positive charges for example. Force on Q2 due to Q1, I will write this one as F21. So how the force looks like, as you have a repulsive force, you have, so Q1 is pushed away. So Q2 is pushed away by Q1. So this is how you write. So this is F21. F21 bar, I want in terms of vector, let's say, I want in terms of vector. So how will you write the Coulomb force? So here R12, right? So I'll assume this direction is R12 cap. So now I will write F21 bar equals to 1 by 4 pi epsilon naught Q1 Q2 by distance between them. What is this distance? R12 square, because that's the distance between them, and then I'll write a unit vector in this direction. What is that unit vector? R12 cap. So cap is a symbol for a unit vector whose magnitude is 1. Unit vector, a vector whose magnitude is 1 and the direction only it will shows. Okay. Very good. So this is the force on 2 due to charge 1. Now we do reverse. Let's look into force on Q1. Force on Q1 due to charge Q2. So this I will write it as F12 bar. So which means Q2 repel Q1 like this. So this symbolically I will write it as 12 bar. This direction in terms of unit vector I can write it as R21 bar. R21 is the distance. So R12 is the distance between 1, 2, R21 is the distance between 2, 1. So both are same charges, right? So the unit vector R12 I gave towards right, R21 I will write towards left. So R21 cap. Okay. So what exactly I am doing here? So this way I wrote R12 cap, and this way I wrote R21 cap. Directions in different directions, and now I wrote the distance between 1, 2 like this. R12 is same as R21 because the distance between 1 or 2 or 2 or 1 is same. So this I can write it as F12 bar equals to 1 by 4 pi epsilon naught Q1 Q2 by R21 square, then R21 cap. Okay. So like this we can write. Now what happens here? So from the diagram it's very clear that R12 bar equals to exactly opposite direction, R21 cap, exactly opposite direction, and the value of R21 equals to R12. So I will use this idea. I will rewrite this one as 1 by 4 pi epsilon naught Q1 Q2 by R. Instead of 2 1 square I will write 1 2 square, and then here R cap. In the place of R21 I will write R12 cap. So if you observe carefully, this one is same as this and this one is same as this, which means this entire thing you can write it as F21 bar with negative. Why negative? Here it is actually negative. So R21 is equivalent to minus R12 cap. So which means this you have to write negative. So finally what I have here is 12 bar is equivalent to 121 bar. So that's the equal and opposite forces. The force on first charge due to second charge is same as force on second charge due to first charge. So they have equal and opposite forces. For example, I'll explain with one example, then you will get more clarity. For example, I have two charges. The first charge is 50 microcoulomb. The second charge is 1 microcoulomb. Which is higher? 50 microcoulomb is higher. Now, let's say both are positive. Both are positive. So you have a repulsion. So 1 microcoulomb will be repelled by 50 microcoulomb, and 50 microcoulomb is also repelled by 1 microcoulomb. Now which one will repel with more force? With more force. 50 microcoulomb repel 1 microcoulomb with more force. If you think like that, it's wrong, because magnitude of force of repulsion between them is same. So that's a magnitude of force of repulsion is same, and it just depends on product Q1 and Q2. So 50 into 1 is the magnitude of product of forces. So the force with which 1 will repel 50 is same as the force with which 50 repel 1 microcoulomb. It's the same force, equal and opposite forces. It's a Newton's third law. Newton's third law. So this is how we can write Coulomb's law in vector form in a straight line.